Hi, welcome back to Book Club. We're in Apply Numerical Methods. And again, you don't necessarily have to do this book. It's a great book. You don't have to necessarily do it with Python. Python's a great language. But, we've been kind of getting through some linear algebra stuff, and I want to do sort of round 2 of linear algebra. How do we actually do this in person, in real life, okay? And so a lot of this comes back to what is really going on with linear algebra. And the way to think of this is, yes, you have some matrix A, some unknown vector equals B. And through the process of, remember, digitization and discretization, we will convert real-world problems into a set of unknowns X, and ultimately a set of forcing functions B and then interactions A. So really this is, the way to think of this is interactions between the X, unknown X vector, and then B is sort of the forcing functions, or the physics, the stimuli is the way the book says it, right? Because it's stimuli. Okay? And to invert this matrix is along operations. So if there are n unknowns, then really, I'll write this in a different color. For n unknowns, to find the solution, to invert it, takes n to the cubed operations. So in the end, this is a thing that we just don't do. Okay, we almost never invert the matrix. Now, if n is small, all right, your computer is way faster than you. Okay, so if n is small, you absolutely should just put it in and just say invert and be done with it. Whether it's MATLAB has got a super easy command, Python's got some easy commands. Really, there's a level beyond which, like, don't worry about it. Honestly, my threshold is like, if something happens under a second, you don't care. If something takes a few seconds, I start to care. And then my next threshold is like 5 minutes, right? So if I hit run and it's cranking, I can go get a cup of coffee or run to the restroom or any of these things. Like, so you have these blocks where you care. And so if something is taking me 5 minutes, and maybe that's kind of annoying, like if I'm really kind of debugging something, I don't want to have all of these 5-minute pauses. I may actually go back in and do some more advanced methods. Okay, and I actually found this great graph that shows some of this, right? So what is the speed up that we have? This is usually called Moore's law down here, just from kind of supercomputing hardware getting faster. And some of this actually accounts for multiple processors as well. This is really kind of a supercomputer format, but there's a whole lot of algorithm speed up that happens as well. And so we're actually going to talk a little bit about some of these. Gauss-Seidel, relaxation, conjugate gate gradient. We're going to talk about some of this. I don't think I'm going to get to multigrid here this time. That's getting a little bit too advanced. But the important part is that we don't really want to solve n cubed all the time. Okay, we actually are going to focus on methods that iterate at n squared. Okay, times some number a. I'll just say a number, and a can vary. A is the number of n squared operations has a lot to do with the properties of the matrix. There's a little bit of the condition number that we were kind of talking about before. So I'm going to get into some of this today. And in order to do some of this, all right, we want to first talk about norms. And norm is a thing we are very used to in 3 dimensions. So a norm, for example, is like a distance. And so if I have a vector A, B, C, and this literally could be a vector that's saying, X, Y, Z coordinates. Here's sort of the length of, this ruler that I've pointed in this direction in some coordinate system that has coordinates ABC. The ruler's going from 0, 0, 0 to ABC, and we have the length of that. We're sort of used to thinking through the length, which would be the square root of A squared plus B squared plus C squared. Okay. Well, this is actually a norm, and if you have, some vector, the book says F, then you can think of this as a norm. So usually it's 2 parallel lines. And the special one here where it's squared, we would call this it's called the Euclidean norm, okay? And it's really after Euclid, the Euclidean norm, which he was the one that came up with distances and things like that. Okay, so that's a very common one. But that works on a vector. What's a norm on a matrix? Okay, well, if you basically just repeat this on a matrix, and what you do is you take the square root, but you sum over all I and j, and you take the ith and jth component and you square it, this is called the Frobenius norm. And so let's spell it correctly. Frobenius norm. Okay, so it's just the sort of the norm you're thinking of, which is just I square all the sum of the squares of a matrix A, and I'll have this number, this norm. It's some sort of measurement. Okay, what is it tied to? Who knows? It's tied to the sum of the squares. It's just a thing we can do. They become useful when we talk about condition numbers and different things like that. So I'm going to kind of finish some of this, but there's a more generic version. There's nothing. What's nice with a vector is you can't think of this as a vector with a length, and square does have value. If it's a matrix, there's nothing magical about square, and so you can actually repeat this. I'll keep it in green. So you can repeat this and say the P norm of matrix A is the same thing, the sum over I and J, but I'm going to take the pth exponent of it, and really this is the pth root, if you will. So there's nothing wrong with that either. Okay, and so one of the a couple unique examples of the P norm. So if I just say what's 1, you have to kind of work through this. Then all you're really doing here is saying the sum over effectively the absolute value. Okay, and then the other one is the infinite norm. And so you have to think to yourself, what the heck is infinite? Well, effectively, this is just going to give you the maximum, right? So if you take A, matrix A, and let's say there's a really large number in A compared to all the rest of them. If I square that large number, the square that's going to be really big compared to all the rest of the squares. And if I cube it to the third power, so what you can eventually, where you can picture is whatever that is, that biggest one, but if you take, the power of this to a really big number, it's going to get so damn big, and then you're going to take the pth root of it. The infinity matrix here is actually literally just what's the maximum value. That's the easiest way to think of it. It's just run through the matrix, what's the maximum value. So it happens to be this limit, but that's okay. All right. And so in the end, one of the things we do with this is we want to have an idea how hard is this to invert, for a couple of reasons. Okay, where it comes in. If it's really hard to invert, then we've talked about this before. What that actually means, so these interactions you can think of as sort of where is the intersection of, say, two lines. And so we've talked about if two lines are really close to being parallel, after I've discretized and digitized on the computer, I actually might not know, and I'll use a different color. Again, you can think of the thickness of my pen as the uncertainty. I actually don't know if that's the answer or if that's the answer. And now, that may not look like a lot, but you can see it even on the screen that those two lines are different. And so two parallel lines where they intersect gets really hard. Okay? And so that's just finding the answer given the fact that we have stored this on a digital computer. That's one way where your error is growing just because of that digitization process. And discretization would be how, maybe this isn't a matrix you came up with. This could be, I'm solving some differential equation that I've converted into a matrix. That would be the discretization problem, okay? But condition number actually drives this number A here. Well, how many guesses is it going to take? I don't want to do n cubed. I want to sort of iteratively come up with guesses, okay? And that's called the condition number. And the condition number is basically right in front of my face here. Condition number. Condition number is if you had the inverse, so this is a little silly, if you took the norm of the inverse and you multiplied it by the norm of the actual matrix, this is condition number. Now, you may say, how the heck is that even useful? I don't have the inverse matrix. Well, it's okay. We can talk about things like being ill-conditioned. It's an observation. We can either observe it because it's really hard to get to an answer, or we can observe it because it's taking too long to get to an answer, or there are ways of estimating this. So I'm not going to get into the ways of estimating this. Most routines, if you actually needed to calculate the condition number, something like MATLAB is going to have some built-in estimates. I think even Python has some ways to build an estimate. But just the concept of condition number really comes back to these kind of two lines that are almost parallel. And so it's both the error in my answer but it can also drive how many iterations it takes to do this. So let's talk about those iterations. What are some of the ways we can iterate? Okay, one is called Gauss-Seidel. Okay, and what you effectively do is say, I want to define my n+1 guess. Right, I'm actually use different information, and so what you do, okay, is you can basically split the matrix in two. So you can say, instead of solving ax equals b, I'm going to solve some matrix. I'll use D for different for a second. I'll come back. It'll save me some time. D matrix on the n+1 plus the A matrix on my nth guess is equal to B. And so if I do this, then ultimately I can start with a guess. I could start with 0, 0, 0 as a guess. Okay, a lot of times, a lot of these routines, if you just call MATLAB or something like that, these routines are literally going to start with 0. Unless you tell it otherwise. You're free to tell it a starting guess. A lot of times they have these options. Okay, so I'm going to use a different matrix here. And then usually, sorry, this to be clear, this is usually not A. This is usually A minus D, if you will. It's sort of the different component. And so in the limit, this is the same thing. So hopefully this converges. And Gauss-Seidel is actually a special version. What we'll actually do first is called Jacobi, where D is actually the diagonal matrix. And so inverting the diagonal matrix is stupid easy, right? We kind of walked through that last time. You just divide by the value. So Jacobi is truly what I wrote up here. So this is actually Jacobi, right? Where you're just using the diagonal matrix. So D would be not different, be diagonal. Okay, Gauss-Seidel is a little bit unique, where Gauss-Seidel is what a human would do. Okay, so a human would actually go through and wouldn't solve for this x vector all at once. I would actually split it up and say, okay, first I'm going to update my guess for x1. So x1 for my second guess. If I start at 2, that's not squared, like second guess. Okay, and I may have some, I'm going to solve that based on my b. Let's say I'm just writing down some numbers that are in the book. I'm going to have some formula x2, 0.2, x3. It's not even important where those numbers come from. It's basically the B matrix and the A matrix. But I'm going to use, this is the first guess and the first guess. So I can put zeros in here, okay? And then I'm going to have the same thing. What's my second guess for x2? I'm going to have all the same stuff here, the numbers for x2, but I'm going to have buried in here, I need to use some guess for x1. And I just finished updating x1, and so I'm going to go ahead and use the newer version of x1 here to calculate x2. So that's Gauss-Seidel. That's a human doing it. What would you do it? The reason I say a computer doesn't do it, it's not that you can't code that up. A computer actually goes back to how computers work. A computer can actually do a whole bunch of operations efficiently if you tell it in advance what you're doing. Okay, and so feeding a computer and doing actually this Jacobi method and saying, no, computer, just take all of my old guess and then just zip through this. It can actually be faster for a computer to do the Jacobi method rather than having it come and do this first and then that first and then that first. And it just really goes back to moving memory onto, from your RAM to your L2 cache to your L1 cache to actually onto the register to compute and then off the CPU. A little bit it's kind of into the structure of computers, which I don't think we've talked too much here. But really, you just really remember from an algorithm point of view, computers are usually pretty bored. Okay, if you're keeping a computer processor at 5 or 10% busy, you're actually doing pretty good. So a lot of that algorithm speed up that I kind of showed here, some of this is actually literally just keeping the computer less bored by feeding it information that it doesn't have to wait. If the computer has to wait on the information it just finished doing, it's going to come off the register, it's going to make its way back around and reload onto the register. That process is not as easy as just loading up the computer with all of this information. I'm just saying crunch away at once and then giving it sort of a longer cycle so it can keep feeding itself better. It's just the way computers work, okay? So that one's interesting. And then if we don't always have to take the guess directly, okay? You don't always have to do that. So there's this whole suite of methods called relaxation that would then say, okay, that's great. before I actually do x n plus 1, like my next guess, I'm actually going to take my old guess, and usually alpha is the term on it, of my x tilde. So x tilde usually refers to this thing. I'm going to run through whatever my algorithm is to get my next guess, but before I actually commit it to being my next guess, sorry, not alpha, 1 minus alpha, I'm going to take only some factor of that compared to the others. Okay, so that's relaxation. And some algorithms will converge faster with a better relaxation. What is that number? Honestly, it depends on what your interactions are. So it's a thing that some algorithms we can actually show having a relaxation parameter is more stable generically. Okay, so a lot of this just comes down to into practice. Different algorithms have different stability characteristics. And again, it's back to that, like, if it's really eating your lunch, then it'll be a thing that you'll dig into. You actually will get into some of these methods to understand, this is really eating my lunch. I need to advance how I'm doing this. Where, again, codes like MATLAB and Python, even to some extent, we've developed algorithms that are fairly generic. You may be able to just kind of call it, and maybe it's taking a minute and you're okay with it. Once it starts getting to those really annoying numbers is when you really start kind of digging in and seeing, is there any advantage I can do or any advanced algorithm I can do? So again, just kind of user dependent, just for your awareness, what's there. And especially if you're just like using a commercial solver, maybe you're doing finite element analysis and it's some commercial solver. This is all happening in the background, and you just are like, this solver is a piece of junk, or the solver is great. And like a lot of times your experience is just based on, did they guess the right algorithm for the problem that you're solving, can completely drive the customer experience, which is crazy. Okay, so a couple more. There's a whole class called conjugate gradient, or really, I'm going to draw this in a sort of a 2D environment here. So this would happen if there's only 2 unknowns. It's really hard to draw things with like 3 unknowns, let alone like a million unknowns. That's a million vector space I can't draw. And so on this axis, let's say here's the true solution, okay? And I can define a residual, which is the right-hand side minus ax to my nth guess. This is the residual. So if I get it, if x is correct, this is 0. So driving residual to 0. So I'm going to plot now contours of residual, right? And so if this is the correct guess, then there might be contours of residual like this. And again, I'm going to use the sort of notion of some sort of norm. What I'm plotting here is some norm of the residual. It doesn't matter what it is, okay? And so conjugate gradient is actually saying don't ever invert this, just use with R. And then if you're interested in the algorithm, you can go look it up. I'm not going to kind of drive through conjugate gradient because you can get it with this drawing. Let's say here's your initial guess, okay? And it's going to pick a direction through this algorithm. Let's just say the direction it picks is this, okay? So now the algorithm is going to march through that direction, and it's going to estimate along that path where is the minimum. And so hopefully visually you can see the minimum here, because this is the bottom. If you zoom out, what I'm drawing here is a bowl. And so along this line, what's the lowest part into the bowl? Well, the answer is that, okay? So the algorithm would say, okay, along that direction, here's your next guess. This is now x, first guess. So first guess or second guess. Then you get here. The algorithm is then going to take an orthogonal direction to this previous guess. In 2D, there is only one orthogonal direction. It's this, okay? And again, some n-dimensional space, that's not it. So you have to kind of look through the algorithm. It's easy. It's not that hard to understand. I'm just trying to do this graphically. And so you would then step in this direction, and again, find where along the pole is it minimum. Well, its minimum looks like that. So that would be guess 3. And then you would say orthogonal. Again, orthogonal is only this direction in 2D. And so there's guess 4. And boom, like so you quickly are actually finding the bottom of the bowl graphically. I'm showing how this works. But you actually did this. Step 1 isn't find the contours of the bowl. It's not. Step 1 is you're actually blind to this. Step 1 is actually here, and you find a line, and then you solve this algorithm that gets you to here. It's sort of, you actually know nothing about the bowl except for how to evaluate it sort of along a line. Anyways, this cool algorithm is called conjugate gradient. And then there's a modification to it called a preconditioned conjugate gradient. And it's kind of this trick before here. It's actually, I'm not going to walk through it, but it's basically instead of solving AX, I can solve a related problem that I have a preconditioner that I can invert, which is kind of like this. Like this is basically saying I can invert D. I don't have to go completely to this just pure right-hand side calculation. I can do a little bit of smart inverting. In fact, one of the preconditioners is just using the diagonal, like literally right here. That's a version of preconditioner. So that's a whole class of methods, pretty good. Okay, and then the last thing I'll just sort of mention is that a lot of this stuff does actually work if your interactions here are nonlinear. What does that mean? These interactions, what can happen is your matrix A can actually be a function of X. It does happen. Fluid mechanics, it happens all the time, okay? There's a nonlinear interaction. Now, many algorithms in fluid mechanics, we will actually push the nonlinear term over to B, and there's some, we'll actually show some of these methods. Okay, and then that's more because of time stepping and stability. But there are some problems where, especially in the finite element world, there are some problems where it's actually you have it here, and there's a world where it's linear, and then you can have some amount of nonlinearity in your finite element solution, like your the structure you're analyzing is allowed to stretch a little bit. So there are absolute times where it makes sense to do this here, and so we actually have this matrix A that's updating. So every time you're guessing, kind of back to this, you would actually take a guess, and then you would update matrix A, and you would take a guess and update matrix A. So sometimes it's useful to update matrix A. Other times it's useful to get that nonlinearity out and somehow shove it into B, and so that you're actually updating B every time. That's okay too. So what happens there in nonlinear, and I'll again just kind of draw this graphically, that if in 2 dimensions, inverting a problem in 2 dimensions is basically solving the intersection of 2 lines, where each line is basically a row of the matrix. Then a nonlinear version, again, kind of drawing it in 2D, is solving for, I'll keep it orange, solving for the interactions of 2 lines that are not straight, okay? Because it's nonlinear based on n. So the same thing's going to happen. Like, so if a human draws this in 2D, that's why 2D is not not representative. You could do more things than the 2D on a computer, but clearly there is a solution there. There's a place where those 2 lines update. The key point, what you can do here, if this was your sort of starting guess, again up here from a coordinate guess point of view, you can linearize sort of each one of these lines, and you can update it. And so this whole method here actually still works okay. You just effectively are doing a linearization around each one. So there's a whole class of nonlinear operations. Newton-Raphson is sort of one of them, that it builds all of this based off of computing the derivatives, and then certain iterations you can kind of drive through. So it actually lets you, as opposed to saying, let me just update matrix A, that's kind of like the sledgehammer version. The other version is taking this and actually using derivatives of this to sort of solve a closer related problem, rather than just sort of hitting it with a hammer and just going straight to solve it for A, because A may be so far off your interactions. So there's some stability there. So if you're in that world and you're doing some nonlinear stuff, yeah, go dig in. Some of that's in the book, talking about the nonlinear interactions. And again, for some of you, this may be all under the hood. You may be, again, just running some sort of commercial software that you just don't know why it's not converging to an answer, or it's converging slower to an answer. You may just not know. Others of you are sort of down in the weeds. You're trying to solve this yourself in some sort of MATLAB or Python thing. And again, you've hit that curve where, okay, I was okay waiting for 5 minutes, but I'm not okay waiting for 5 hours, and you need to go to the next level. So, that's part of why I find numerical methods just so exciting, because even though, what I do in the real world, I build rockets and rocket engines and all this stuff, that there's so much of this stuff that I do in a sandbox, if you will, on my computer. I'm trying to calculate things. I'm trying to estimate things. It could be the size of the rocket, the performance of the rocket, different systems. So much of this is actually such a great tool set for any engineer. And this is like, again, even though as a professor, what I did was massive computation parallels. That's why I'm very familiar with this world. Right? What I'm doing right now, as the CTO of Venus, is building detonation engines. It's very much real stuff. I don't touch computation at all, except I still have all these tools, and I actually do. I actually use all of this almost on a daily basis, all this numerical method stuff to estimate, to guess, to size some things, to figure some stuff out. So it's what's worth knowing no matter what you think your career is going to be doing. So dig in, have fun. I will see you next time.